I'll do that. So, Tamland. This came up when Stephanie suddenly nobody was available, and then Stephanie and Matt needed to review things that I threw at them, and they'd never seen Tamland before. So I think this is a little bit of an introduction about what it does and how it does it. So where shall we start? Any suggestions on where to start? So we start with the source metrics and the saturation points in the runbooks? That's okay.
Sure.
Yeah, sounds good. I was planning on having a pairing session with you, but not here. not to waste everyone else's time.
No, but then let's whatever you think about when we are looking at things, like throw it out, because yeah, I don't know what to talk about neither, and I've just been doing stuff. So the run books, we have these things called saturation points in our run books. Look at the Redis CPU. That was the one that I was recently looking at, and the point of these metrics that we define, like the query that we define here, is it's supposed to spit out a percentage, so a number between 0 and 1. 0 is excellent, 1 is burning. And then we set SLOs on that, where this is where we're going to alert. That's a short-term thing. We generate alerts from these metrics, so as soon as this goes above this SLO, then the on-call gets an alert. What we also do, so from that we generate a whole bunch of saturation metrics, and these are the alerts. Yes, so those basically just wrap the query that you just saw on the left. Let's look for the Redis one here. So those wrap the query that we've defined here on the left into the thing on the right, and it records GitLab component saturation ratio, and that's the thing that we're going to be using in Tamland. Yeah, so switching over to Tamland. We
don't save that file.
Oh yeah, I won't. So Tamland. Tamland is like an IPython book, so Jupyter notebook, and let's pick the Redis one since we're following that around.
Yeah,
and here
this is the piece I'd love extra details on. I haven't worked with Jupyter notebooks at all.
Okay, so it's funny because these are not okay. Normally, you'd write the markdown file for a Jupyter notebook, and the code cells are Python that gets executed. We generate our markdown files, and this is from service.md.ninja. So that's the template for this file. The front matter is yeah, just like an introduction to, like, that's the rendered on every page, not super important. It's this bit. Then these imports, saturation forecast and operation forecast, that's both of the sections that are going to be on the page. If you look at the page, let's open up the Redis one. Redis. So first we've got the Redis non-horizontally scalable resources. Those are here's the primary CPU one that we were looking at before, and that comes from this part here. So, well, this part here actually. What I selected here on the right, we do that for each component. We know each component, like Redis primary CPU is one component. We know each component because we generate like a manifest that's here in saturation.json. And that's just a dump of what you just saw in the runbooks repository. That's synced every week, I think. But there's a bot creating merge requests for us. Every time saturation points and so on change, this manifest gets updated. And that's what we use to generate this markdown file that here in the components dict has every every saturation point that we pass in. Are we following along?
Yes. So we're only using the component level saturation and the operation rate. Those are the only two.
Yes, operation rates are a little bit different because here we just select all of the operation rates for a certain service, and we use the GitLab component operation rate. Like so, for every SLI, this is less clever because here we know which ones we should have. The horizontally and the non-horizontally scalable ones. So we know which one we should have, and we print it all out in this, like we render it all out in this dictionary.
I see. So this is a subset then of the. Okay, that makes sense.
Yes. So if you see here, it reaches out into this saturation forecast.plot series method, and it prints out this component stick. So let's go there.
Okay, this is the other piece I wanted to see, the saturation forecasting. I've worked with a few different systems that attempt poorly to do forecasting, and I wanted to learn more about what forecasting method we're using here.
Yeah, sadly, I won't be able to dig into that very much because we use the Profit one from Facebook, but I'll show you where it starts, and then we can dig into that maybe together in a pairing session. That would be cool.
Yeah, okay.
But there's also a cool white paper about profit forecasting that's on their website that I tried to read some of, and then it got into math, and then I stopped. But
okay, cool.
So let's go ahead, Matt.
I wanted to let you finish, and then I had a couple of topics to kind of explore as kind of tangents. So keep going. This is fantastic.
Okay, so first saturation forecast. That's the like we do the separation thing, but all of the component saturation metrics. So those ratios that I just shown you in the runbooks, those get rendered out in these two first topics, and they're basically the same. One has a hard line, ones are marked horizontally scalable and the others aren't. And we treat the non-horizontally scalable ones as more important because that's more difficult to scale, so we want to look at them first. So then let's go into the saturation forecasting itself. And the plot series method is what we're looking at. And so we get the page name. That's all stuff that's just used for the report. Here's the component stick. That's this huge dictionary that you saw on the other side that we pass in. And then for each component, we do a plot forecast. Plot forecast is here. And what that's doing is getting a bunch of the properties of that component to know here which query to build. So like removing the outer join labels, it's removing the threshold because that's not part of the labels in the that are on the series. And then we get the capacity planning strategy to know to know which I can show you that in the load historical data frame, to know which metric we're going to use. Like we have these quantiles. This is the the default one that we use. So we take the 95th quantile over 1 hour of a ratio, and we use that as a data point. Does that make sense? When we specify other capacity planning strategies, then we pick another query. But this is the query that we're going to be performing in the end. The series passed in here. It takes the dictionary that we just saw, and whatever's left in it, it gets turned into the label, so the selector. Yeah, I don't think that's super interesting to show, but that gets, yeah, here, added to the selector. And then we perform a batched query. Let me open from query. Batched query range. So we pass in the query that we just built here on the left, and then the start date and the end date. Timeland uses a 180-day history. So we load all the data from 180 days ago to yesterday at midnight. Yeah, yesterday end of day.
Just out of curiosity, where is that 180 days specified?
That is in an environment variable. Let's start again at plot series.
So it's uniform for all of the series that we're working with?
Yes, it's uniform for all of them. We use the same graph, and then when they're aligned, we're looking at the same data everywhere. Forecasting forecast dates.
That's all I needed to know. Thanks.
Okay, but it's an environment variable, and now that we have the cache, we could extend it. But yeah. So where was I? Querying with ranges.
So I have a question that maybe is obvious, but maybe not. Where is the cache being used by this? Is it getting this query out of the cache?
I'll show you. I was just
okay.
Let's keep walking through. Like that's where we're going to end up.
I'm fine.
Here. So what we do is we batch the thing. So 180 days we can't load into yeah, we can't load it in one query from Thanos. Maybe after Matt and Igor are done with Thanos Compactor, we would be able to, but I don't think so. So we batch this in 180 days, and we load 24 data points, step 3600. That's the resolution that we're using. So we load 24 data points per chunk of 1 day, and the chunk of 1 day is defined.
This is fascinating. So Thanos query also breaks up the Thanos component called Thanos query also breaks up large time spans into smaller ranges for caching purposes. So we're doing something similar here in Timeland.
Yes.
Okay.
Apparently, I didn't know that. Well,
I just learned about this fairly recently. Thanks to some
me too.
Influence.
thanks to Igor walking me through them, because you can have overlap in Thanos at that point, because you have the raw data and the downsampled data which have the same.
Yes.
Yeah.
Exactly.
So yeah, there we go. We separate it into days, and then we iterate through all of the days. This is the loop that iterates, and we stop if if we've reached the last date that we need to get. Now, as for the cache, every query, every ranged query like this is cached. So we do that query range with cache. Here it is. So usually we don't ignore cache for anything anymore. Yes, we don't ignore cache for anything anymore. We used to do that because we were loading up to the future, as in today, midnight, but yeah, we don't have that data. So then we ignored the cache to not have an incomplete fragment in the cache. But we don't we don't do that anymore. So we have this prom cache manager thing that takes the query and the from and to date time. This is already sliced up. So here this from and to will be 24 hours long, and the step is going to be 3600. So the 24 data frames. And then we try to read from it. The cache manager. It's going to be this one, I think. Yep, here we go. So that just what does it? Yeah, it loads the it loads the entire day and returns that data frame. And a data frame is a pandas data frame. A pandas data frame is the library that we use to query Prometheus and so on. So it returns exactly the same thing as we would have if we query. Here query range would retry would return the same kind of data frame, and we write
so
it. Yes.
So it's serializing the response from
Yes.
we're querying this through Thanos.
into these kind of Parquet files.
Okay.
Here you can see the structure of the. Actually, it's maybe nicer if I show you.
And the width of these individual what were we calling them? Chunks or ranges?
The width of this. Wait, the width of this data frame returned is 1 day.
Yes. Okay. Great. And that I'm just realizing that earlier you mentioned that we sync the the definitions for our saturation thresholds on a I think you said a daily basis. Maybe you said a weekly basis.
Maybe weekly, maybe daily. I don't remember.
Okay.
Yeah.
I was just kind of thinking about the like if we made sorry this I said that I'd hold questions. So let's keep going with this.
No. I see where you're going. I think there is likely something to go wrong with the invalid cache if we change the same metric to be different suddenly.
Yes.
But
like
we also can't
changes to the metric. Yeah.
Yes, but we also don't rewrite recordings for those metrics, and those are recorded. So that it's a kind of a moot point. What we have done in the past for changing saturation points is introducing new versions. So we add a new version, run both of them side by side because Tamland wants
enough history to do the projections.
Yes, more than 2 weeks of data. So more than 14 days of data before doing projections, and otherwise we just ignore the component.
Yes. Okay. Makes sense.
Yeah. So we
awesome.
Read,
okay.
We read and then we go through the cache, and the cache looks like this. So these, and this is the part of the thing that I might want to change. These are like hash of the query. So exactly the query string that we pass into Thanos. This is it. SHA-265 or something like that. And then for each query, we've got the day. So here we can see the query. This is the query that we were doing. Like here, it's a utilization metric that I didn't want to talk about just now, but yeah. So the query is there in the file, and then these are the days in Parquet. So that's like, the format that it's stored in. Yeah.
And where were you looking at this? Is this the directory structure you were just showing us? Is that
this is just stored as a directory?
Okay, in the Git repo. Okay.
And no, not in the Git repo. It's not checked in. It's
okay.
It's written and ignored, but we have this task. So this is how it loads the data. Do you want me to continue from here and go into how it gets the data and caches the data and make sure that this thing doesn't take 6 hours to run? Or do you want me to continue into the forecasting bit?
Let's skip the forecasting for now and continue with the mechanics.
Okay. So
does that sound okay to you, Stephanie?
Yeah, totally.
Okay.
So here the query gets cache hit up, and if it isn't, it's there. It's written query with range. Yeah. So here query is none, cache missed. We perform the query with retries. So if there's one failing, then we try again. When we do get the data frame, we write it out, and that happens here in the directory structure that I just mentioned to you. Yeah. Then we have got an entire directory full of all of these files, and if to make sure that we don't need to redo this every day, we've got this populate cache command, which does, like, as you remember, we went into this coming from the book that performs a bunch of queries, and at some point it hits the query range with cache method. Here we're coming at it from the other side, so we don't start from the book, but we start from this script. And here let's go for, we were talking about saturation components, so here are all components in all saturation components. All saturation components here are basically generating every page like we generate like from the Ninja files. So it gets all of these components in all of the sections. Yeah. So what goes in here are the same kind of component libraries. Component dict, if you remember the name, goes in here, and we build this array of components, which means we start with the same thing. We've collected all those here, and then so here we've collected all those, and then we tell him populate the saturation component for each of those. All of this here with the futures and so on is and the thread pool executor is a way of doing this synchronously, because most of the time, most of the data is cached for 180 days, only one day is not cached. So we do this in several threads to just iterate over all this, like spin our wheels for over the 197 days of data that we're going to load, see if it's all there, and if it's not, we'll populate it. But we limit it to 5 to when we do hit the new day to not have a thundering herd on Thanos.
Yes.
So here's the populate saturation component, and you see here that it takes the same plot forecast method that we just saw, and it does this thing with from to, which are the same forecasting dates here to load all of that. So it's going to go through all of this cache manager stuff here and write out the data directory. This skips generating the forecast, which also takes some time. So it's slightly faster than running the entire book. It skips that's with the historical only here, skips calculating the forecast. The forecast, I'll get to it later. Yeah. So now we've got a fully populated data directory, and then what we do, this gets run from a CI job. So GitLab CI, populate cache. So we have this thing that extends build with cache. Here it is, and that starts by downloading the cache, what we already have. That's downloading it from a generic package. So it's a GitLab feature. I can show you that here.
So this is like a tarball or something?
Yep, exactly.
Okay.
Lives in the package registry here. So right now, 27 megabytes of data compressed is in there. As you've seen, like it compresses quite well. So first we download that, then we run that makefile that I've just walked you through. We populate the data directory some more. We upload a new one and we remove the previous one. That's how the cache gets populated. Any questions here before we go back to the forecasting bit?
That's absolutely makes sense. Thanks so much.
Then saturation forecasting. So we took a tangent here when we hit the load historical data frame. That loads a data frame for the entire 180 days. Then if we're not coming from the cache thing, this historical only thing is set to true for populating the cache, and when we're rendering the book it's false. So then we're going to generate a forecast, and this is where the smarts happens. This profit is a little bit of a black box that you can add some parameters to, and that's going to make future data frame. That's going to make the same kind of pandas data frames like we got from the Prometheus queries. So we've got the same kind of things. We could actually write them out the same way if we wanted to, but those might change obviously, so we don't. And then we wrap it into this forecast object.
I'm probably just missing it, but how do I pass in the input data for Profit to consume? I see where we're configuring daily and weekly seasonality.
Yes, wait a second. Plot forecast. That's how we configure it.
How does it know where to get the input data?
So here's the data frame. We pass it in here.
Oh, DF.
Here,
okay.
DF, and then we do. There should be a forecast or a predict call or something.
Oh, m.fit maybe. Yes. Okay. But 5 lines down.
Yes.
Okay.
So this is
Yes. Okay. Fantastic.
black box. I don't know.
Okay.
the smarts, but yeah.
All right. Cool.
And then here in forecast, we basically prepare it for rendering out in a pretty graph.
Yeah.
Pretty eye of the beholder and so on, but
yeah.
So the configuration of the axis, the graph lives in here. So
this is fantastic tour. Thank you. This was the end of the line, right?
Yeah, I think this is not what I had planned, but it's where I ended up.
Okay, no, that's fantastic. So one of the there were a couple of things I wanted to I guess I'm not sure if I want to chat about this or brainstorm about it or just kind of keep an eye out for ways to handle it gracefully. When I manually look at the trending history for even outside of Tameland, just for any kind of time-oriented trending behavior, some common classes of gotchas that I've run into are, I'm sure we've all run into, are having a discrete event like a change in system behavior where like a workload change or an efficiency or inefficiency was introduced, or a defect in the measurement was corrected. it would be really, really useful, I feel like, to be able to annotate that. And in Grafana, we can add annotations, but I don't know if we can add annotations to Tameland.
We can. Well, Prophet supports it, so that means that, like, I don't know the code by heart, but I've seen it in the documentation that you can do in this. Like here, like we said, the daily seasonality, we can add like ranges of that we need to ignore. So that's possible, like ignore or do something else with, like, it's supported, but we don't have a way of doing it right now. So when we have these things in Tamland and we see them as a human on the graphs, then we currently say this was this, park this issue for like how long we think, like if it was like a 1 week thing, it might take a month or so before the prediction is like over it.
Yeah, I guess I was wondering if. Yeah, that makes sense. So I was kind of thinking of this as kind of a twofold topic. One is kind of conveying, like, when we do this kind of discovery work, it's nice to be able to pass that along to other humans, like we are right now. Or if since we've got a rotation now, being able, having a place to kind of say, hey, for this particular, I guess they're not really alerts, but for this alert, here's what I found. This will probably continue to affect the projections for the next n weeks or whatever.
Right now this all lives in those issues, but I think ideally, and I haven't created an issue for that, we would fix the prediction. Like we only have 1 week, like this thing happened.
That's the other thing
we did database maintenance, or we were close to saturation because this thing got deployed and it burned up Gitlab. We know 3 days are bad, ignore these 3 days, and then the next prediction will be like we'll see the dots of the actual data when we like these dots.
Sometimes when we have so I guess ignoring a particular range lets us handle things like a discrete event that caused an abrupt limited duration spike or dip,
an explained one.
Exactly. What about cases where like, for example, we made a capacity increase, which dropped the percentage utilization, or we made an efficiency increase, which also drops the percent utilization, like we have with, like when we added capacity when we added memory to Redis cache, or when we performed tuning, or when we offloaded reduced the TTL for Redis cache. I'm just thinking of kind of recent events, and we do this in a bunch of different components, largely as incident response, but sometimes as like planned work as well. How do do you know of a way to kind of retrain the projections to like where we can give it a hint that says this was a discrete event that will have a lasting change?
Wouldn't the projections just magically fix themselves at that point in time? I mean,
but it takes a while. If you do a thing like
this is why I want to see the algorithm that we're using, because
let's look at the Redis thing. No, yes, the Redis cache.
That was, when did we do the Redis cache work? A month ago? A little over a month ago?
So Redis cache, what do we do? You can't see my screen.
But we're sure it's very good. Whatever you're showing us is very useful.
It's me scrolling through a page. So here's the Redis memory. No.
Right.
Okay. That
this is a problem because we didn't have the saturation graphs turned on before
yes,
Redis
exactly.
cache.
Yeah. We said
we turned it on as part of that work.
Yeah, no, we had that before, and we said we don't need this for Redis cache because it's always at max memory, and that's what max memory is for. And then we decided it's not what max memory is for, so we do need that metric, and then we introduced it. But this is the kind of event that Matt is talking about.
Yes, but the confidence bands are just way out of whack.
let's like we saw this coming, so we did the thing, and we had this drop. Now be smarter about it. Like it's going to grow at the same rate, but yeah. And I was looking.
Wouldn't Redis CPU? I think Redis CPU was already being tracked, wasn't it? Redis cache CPU.
Oh yeah, let's look at that too.
because that's the one I looked at some of this yesterday. I'm not.
Oh,
It's
yeah,
not just that I was that smart.
that's a great idea, though. When we changed the machine type, that doubled the capacity.
Yeah. Let's have a
There you go.
single node, but we want the primary. What was Redis primary? Yeah.
There you
So
go.
here, it's not as dramatic as you would hope, but like these things, these outliers. So yes, the trend is going to go downish.
Oh, wait, this Redis primary CPU resource, that's going to be the Redis
It's-
main thread, I think. So
Yeah,
Yes,
it's still a
it's not
single
gonna be-
CPU.
yeah, it won't be sensitive to having more cores.
No.
And I don't think we upgraded or changed the CPU
Right. Type.
size or
No.
speed or anything else. So yeah, okay,
And the
never
other
mind.
one, the other Redis, like if you look at the since it's single core, single threaded, I mean, then
You scrolled past. I didn't catch what it was, but just when the screen was refreshing, there was one of the graphs that had an abrupt drop in the and it had the confidence bands arc out.
this one.
Yes, that was the shape I was looking for. What is it? Oh, yes, the memory resource utilization. Yes.
So that is actually, isn't that
That's what we
what
did.
we were looking at? Yeah.
So then these confidence
Max
bands are
memory.
way out of bound, and right now we
Yes.
deal with that humanly. Like humans say,
Yeah.
no, we've got this. Like it often happens. We create the issue when these blue bands hit the red one. Then we create a capacity planning issue.
Yeah.
There's so much stuff that I still haven't shown. Like you don't know how these pages get generated or
Yeah.
how these issues get created with capacity planning.
I have a question that is probably a very simple yes or no one at this point in time. At this point in time, we're only focused on capacity planning in the sense of something is going to get too big, correct? We're not actually looking in any way at we are wasting resources on this and should use. Yeah, okay.
No, but no, we don't have anything for that. It's just things will stop working if we don't.
Right. I talked to Blake for a while yesterday, and it seems like we are wasting resources on this would be something that Tamlin might potentially be useful for as well.
Yes, for some things, if the
There, it's obviously dependent on
way
what the
out
things
like
are.
but if
Yeah.
you look at, I can show you one. I think if I look for trace chunks.
Yeah, there was a couple scrolling through those pages that looked very obviously like we're just throwing a bunch of resources at something that isn't using any of it.
Yeah, I mean these graphs give no context though. So like
correct, and that's
yeah.
why I'm asking the question, not saying it's a thing we should do.
Yeah, like I mean, Redis being a great example of a case where we have a bunch of CPUs on some of these Redis boxes,
right?
Even though Redis can't use the CPUs, but
Correct.
implicitly by having a bunch of CPUs, we also
We have a
get
more
a bunch of
powerful
memory,
machine.
and we get prioritized network throughput because that's also stupidly tied to number of CPUs. I mean, from our perspective,
absolutely,
it's funny, but from the more the machine type and it is. I mean, I can kind of rationalize why GCP does it this way, but I find it kind of distasteful.
But like from that perspective, what we're seeing here on my screen is the single threaded, so single core CPU for Redis trace chunks, and I bet that's exactly what you were talking about, because we provisioned that machine to handle a lot of throughput, like network throughput. But for the rest, it's sleeping.
Exactly. So we can like in using the trace chunks as an example, we can do an assessment of like. I guess what I'm trying to work. This is such an interesting topic. So we have kind of just thinking of like VMs as a collection of a handful of different resource types.
Right.
And they get. I mean, the way we provision these VMs is generally in kind of standard kind of blocks of those resources. So if you want a machine of size X, then you're going to get this much CPU and this much memory and this much network and this much disk. And we don't have to do it that way, but that's a common provisioning approach. And I guess what I'm kind of working up towards is for a given workload, whatever workload means in the context of the service that we're talking about, there are generally going to be as human analysts, we can identify certain factors that are likely to influence. I guess what I'm getting up to is there's always going to be at least one resource that is the most critical bottleneck for a given workload, and
then we pick resources.
Yes, exactly.
Based on
that. Exactly. So from my perspective, what I'd ideally like as a team for us to be able to work towards is building a knowledge base of what the bounding resources are for given workloads and services. What factors influence changes in that workload, because changes in the workload drive changes in resource utilization and can shift the bottleneck to some other resource or component. And being aware of that is just solid gold in terms of being able to do both capacity planning and incident response. Reduce cost, exactly.
Yep.
So
yeah, they're all related.
Yes, exactly. So that's like, I don't know how much of that Tamlin can help us with, but in terms of like, as a team of human engineers, that's what I would ideally like us to be able to move towards, using whatever the right tools are for that kind of work. That's kind of my personal ambition for us to be able to accomplish as a team. I mean, but that's just one person's opinion. So I was really curious how you two felt about that as kind of one of our something to work towards, and also thoughts on how we can kind of begin to accumulate this kind of information in a
structured
like
way.
Exactly.
Because it's this thing that we just talked about with redis trace chunks, we reason about, and that's
yes.
But how does somebody, like, for example, Blake, go past the graph like this and say, whoa, the CPU is not utilized, why is that?
Yes.
Reason about this.
Exactly. I kind of feel like this, having kind of a set of a set of kind of notes about bounding resources and known factors that influence utilization of those resources could be organized on kind of a per service basis. And I had at one time a couple of years ago thought that we might use the runbooks for that, because we have sort of a similar need in terms of incident response to do service oriented triage. The runbooks are kind of a mess in terms of the the organizations, not lacking. There's been several kind of attempts to tidy that up. So I guess what I'm kind of working up to is I don't really care where we put it as long as it's accessible to folks, and we have enough freedom to organize it as. The more we do, the more we'll understand about what structure is useful for our purposes for doing analysis and forecasting. And I think once we kind of have done a little bit more of this as a group, it'll be more clear what aspects of organizing this information is useful and reusable. In past work prior to GitLab, we used a wiki for this. We're not big on wikis here. But,
and the problem with that is that I always find that all of them fall out of date pretty quickly. Like the thing for me on anything like this is we need humans in order to determine what the bounding resource or resources are. Yes. But I would want the way to discover that for future humans and the way to keep that updated to be programmatic in some fashion. Like, I don't know what it would be. I don't know how we could do it, but in some fashion, I would like this.
What do you like? Because now I'm thinking like, starting this out like everything in the run books and saying API, like the web everything there is mostly memory bound.
Right.
And we just mark that on the service.
That's kind of what I'm thinking is, do we label it in Prometheus in some fashion? Do we
Well, as soon as it's
put
there,
it
we can label it, but is that
Right.
going to go out of date with the workload changes that Matt was talking about?
Right,
Like
right.
It might.
how often does that change for
But
Redis for
I mean, I don't think Redis has two,
memory and CPU,
correct?
and for cache is going to be for cache is both.
Well,
Yeah, for all of them, it's both. That's
Gitlab
the
is maybe an
problem.
interesting service because depending on like we can drive Gitlab to CPU and memory saturation either at the same time or separately. Like there are known workload patterns. Exactly. Yeah, exactly. Like representing a kind of a cascading failure scenario. Like I'm gonna just to have a concrete example to talk about. Now that we've rolled out C groups, there's a pattern where I mean this can happen without C groups too, but it's easier to talk about in the context of a C group. So you get one project that has say someone's got a fork of Linux kernel or a fork of GitLab or GitLab, something that's got a lot of Git objects in its history, and they do I shouldn't talk about the specific mechanics of this particular kind of abuse, but say they run some gRPCs that are particularly memory intensive and require a long-lasting traversal of the object history, and that drives up both CPU and memory utilization. But in this context, we're going to imagine that we run out of memory first. This anonymous memory usage depletes the file system cache in whatever scope we're working in. In this case, suppose it's a C group. So just to put some numbers on it, these numbers are smaller than what's in production, but say we've got a 10 gigabyte budget for memory in the C group, and normally that's plenty. Normally that's mostly file system cache pages. But when we run this particular workload, each time this gRPC gets called, it gobbles up, say, 4 gigabytes of anonymous memory and holds it for a minute. So if you get two or three of these running concurrently, then you've just kicked out the entire file system cache. And at that point, any other action, whether it's these poisonous commands or not, has to do a lot of more disk I/O. So at that point, we've shifted the constraining resource from memory to disk to block I/O. For the scope of the project that runs in that C group. I'm not sure how we capture that, but as humans, we can write some prose that describes this pathology, but I don't know how we capture that in a forecasting framework, except it does have some interesting properties like that state transition where we abruptly switch to having a large increase in block I/O. I guess this particular the scenario I'm kind of talking about is like more of an incident, but if it becomes a recurring pattern, then I guess we could think about it from a capacity planning standpoint as well.
We do like the way we match these saturation points to services is like through tags.
Okay.
Show. It's a bad example now, but like, do we already have saturation metrics for the newly introduced C groups? And do we need them?
No, we don't have new saturation metrics for it. We're relying on the host level metrics, and the reasoning for that is it's really difficult to measure accurately how much.
Yeah, because these are container like. Yeah,
exactly. For memory in particular, we it's normal for the C groups to have approximately 100% memory usage, but most of that memory should be file system cache pages, not anonymous memory. So that's differentiating between different types of memory usage. C Advisor doesn't do a fantastic job of advertising the way in which memory is used. So it's kind of like at the host level where for Linux on like some OSs. Linux prefers to have a very small amount of actually totally unused free memory, but it'll use most of its memory for custom cache, and it'll give up those pages whenever processes need to allocate anonymous memory.
Right. But so what I was driving at is that we have a mapping of which services depend on which of these resources that could get saturated.
Okay.
Applies to here. So for example, here's the CPU saturation one that is using the metrics catalog to find everything that is provisioned on VMs, and that's based on let's go to no, what is still on VMs, Gitlab? So here so we've got these tags for some Go things, and then we've also got deployment. I thought that was marked somewhere. Neither of you remember how that's marked?
No, I'm not quite sure what we're looking for at this point.
This thing that also like it's a stanza that's in this thing that says this is deployed on VMs, this is deployed on Kubernetes. Here, no, that's service dependencies. Here, cube resources, if that's present, yeah. I think it's something like that.
Okay.
So, well, what I was getting at was, you know, which resources apply to which services. Now we need to group them into, like, we need to group everything into like the bucket of this goes together. This is the same node pool. This is the same node.
Oh, okay. So you're thinking about. I think what you're getting at is in the context of Kubernetes node pools, we may have some heterogeneous workloads where you've got some pods that are doing API work and some pods that are doing that are handling web requests.
It could also explain the situation we were looking at with the rate limiting instance. If we had this grouping and we see like the CPU is underutilized, but it's at the max of its network throughput in the same bucket of resources that we're looking at, then this needs to stay on this over-provisioned machine because of this reason.
Got it. Yes. Okay. Yeah. I was thinking you were working up towards contention between services that are sharing the resources of a single VM.
I think we're far away from being able to do that. That was the thing. Like that's the dream, right? Like right, this Redis thing is not doing quite so much. Let's put some CPU intensive sidekick jobs on it. Like sounds brilliant, but it's very scary.
Yes, I'm remembering some bad outcomes from. Yes, agreed. Okay.
Yeah, I don't know where I was going with this, but. So grouping, having some way to annotate to, like, you know, to Blake as another consumer of this data, to show that these resources are collectively provisioned, and among these 5 resources, this is the one that's a banding resource, and the other resources kind of come along for the ride. Yeah, but as soon as we can already see it in aggregate, I think it's much easier for a human to reason about. Like we could build the view.
Sometimes, sometimes it's hard though. Like sometimes you just seeing the graph and the collection of related graphs isn't enough. You need to see some more about the reasoning. Like for example, we just I think the 3 of us were just had an example of this a couple of days ago, where we were trying to reason about the sizing for the VMs for the Redis rate limiting pods to run on, and we kind of rehashed in kind of rapid fashion the series of discoveries that, you know, from like the last couple of years, where we're like, okay, so we know that, like, you know, the copy on writes during RDB backups means that we need to, you know, have up to double the max memory, and we also have the, more recently we learned about the Redis replication buffer times number of replicas being a factor for certain workloads that take, like Redis cache in particular is big enough that was something we had to pay attention to, whereas smaller Redis clusters we didn't have to. So I think having this kind of, I feel a little bad about this, but this makes me feel like we need a place to put some written prose to describe the interactions between these resources and kind of the reasoning behind why they're sized this way. Does that make sense? I'm thinking of this, I guess I'm kind of thinking of this again in the context of having like service specific, descriptions of the concise descriptions of the reasoning behind the sizing decisions of a given set of resources. Whether that set of resources is like, all of the metrics representing resources for a given VM or type of VM, or if it's kind of in a more abstract fashion. Like most of the time when we're talking about resources, we're talking about like machine resources, CPU, memory, network, disk. But there are of course other kinds of resources like
GCP quota.
Yeah, exactly. So that also, I think, benefits from having a little bit of context around some sizing and scaling choices. Like, I guess I started off thinking about. Sorry, I'm not leading up to anything. I'm just kind of talking talking through. Having like there are a lot of people that are contributing to decisions about how we're making tuning and optimization trade-off choices. So we're not going to be able to capture all of that. But as we're doing capacity reviews, a subset of those are going to make a meaningful impact on the graphs that we're looking at. And as we kind of uncover, like we have an unexpected drop or rise in one of our graphs for the timeline trending. We're going to kind of rediscover, I think, some of those decisions being made, and having a way or a place to kind of and maybe this starts off as just the timeline issues themselves, where
this
we
already
kind of
comes
jot
up in
down.
those timeline issues. Like one example that like a saturation metric that I've been recently looking at is the PG Bouncer one, and that's tied to the PG Bouncer client connections, tied to the CPU of the replicas. So we need to, but like you don't see that context. So you see the client connections were running out, so let's just add some more. But that's not always the right decision, or because maybe this resource was set the way it's set because of, and that's what we need to capture, and that's what we need to be able to have in. So what we want to link is two saturation points that belong together, like that are dependent on each other. Is that?
I'm gonna go drop off and learn about being on call. But I'll watch the last 2 minutes of this if you keep talking.
Okay.
Yeah, I need to drop off as well, but I think it's a very interesting thing that we got into, Matt, thanks to you. Like seeing this, like we need to, what we're trying to solve is not everybody is able to rebuild the context all of the time of decisions that's being made.
Exactly.
So we need to, like, we can't do that. We can't programmatically do that. That's never going to work. But we can give them as much information and like as fast as possible as they need to.
So we don't have to solve this right now, but I kind of wanted to kind of throw it out there, and kind of we could reconvene, because like we're all in this rotation. So now, so we'll.
It's going to be great. Like I've not left you in a pretty good place, but let's pair next week somewhere.
Okay.
On doing a run through, and I'll do a run through and make sure that a book is ready. But I broke things the past 2 weeks, and it was like that's the part that I haven't shown, and I actually wanted to talk with Sean about. But like the bits and pieces with pipelines on Ops and pipelines on GitLab, and the pages side on GitLab, and the two different projects, capacity planning and Timeland. And then the
Yes.
scalability project is adding images to the Timeland issues. So it's a little bit of a, yeah.
Got it. Yes.
But
Awesome. Yeah, I would love to get a walkthrough. Yeah, I just barely started to look through some of the issues, and it was kind of clear that there was some context I was missing. So I thought pairing on it for for the first round or so would be super helpful.
yeah, I'm going to drop something on your calendar on Monday evening or something. Does that work?
Okay. Absolutely. Yeah.
Cool. Around this time?
Sure. Sounds great.
Excellent.
Wait. I'm so sorry. My contractors will be here. I need to look at my.
I'll drop something on your calendar and you move it around.
Okay. Perfect. Yeah, because they won't need me the whole time. I just have to be able to let them in the house.
Yeah. Wait, if it's just for that, you can like tell me that.
Yeah. True. Okay. Awesome. All right. Thank you so much, Bob. This is so helpful.
I need to drop off. Bye.
Bye.